All right, here's some answers for some questions that'll be posed for Wednesday in class. So we're going to draw slope fields first. One's for a linear equation, and starting with this linear equation, since the derivative is already equal to 1 half x plus 1, we just set the derivative equal to 0. We solve for x, and we find that x is equal to -2 as a horizontal tangent. So on our y and x axis, we go to where x is equal to -2, and we draw a horizontal tangent every single place. We also go and we take a look at the two intervals to the left of -2 and to the right of -2. If we plug in numbers to the left of -2, such as -3, we find out that that value, -3 halves plus 1, is negative, so it's decreasing. So the slopes to the left of those are decreasing. If we plug in a number to the right of -2, such as 0, we find, or for that matter, -1, we find out that negative 1 half plus 1 or 0 plus 1 are both positive. So we plug those in and we see that those slopes are positive. If we looked at actual numbers, we can plug in the fact that if I looked at 2 here, 2 times 1 would be, 2 times 1 half here would be 1, plus 1 would be 2. So for the x value of 2 out here, all these slopes would be rise over 1, 2 over 1, and they would be positive. The farther I get away from my critical number, the steeper they are. All right. Let's go take a look at a quadratic of some sort. Dy dx is equal to x squared minus 4. So if we have dy dx is equal to x squared minus 4, we set that derivative equal to 0. We find out that x plus 2 and x minus 2 are the two factors. And if they're equal to 0, it sets us up with the following intervals. First of all, -2, oops, this should say -2 right here. -2 and +2 are both horizontal tangents. So again, looking at my xy plane, I have horizontal tangents at x is equal to -2 and x is equal to +2. And then we got to see what the slopes look like. Again, we looked at our test points here. Somewhere in the interval from -infinity to -2, we plugged in as test point, and we found out that those numbers are positive. In between, and I'm sorry, this is -2 to +2. In between here, I picked a test point of 0, and we found out by plugging those into the derivative that 0 squared minus 4, of course, is negative. So anything in between these two horizontal slopes is negative. And on to the right of that, anything is again positive. So the slopes look like this. They look like they have a max first, and then they come down and they have a min second, then they head back up again. So at some point in time, one of those equations would fit. Let's look at quick cosine x for a moment. So if we set dy dx equal to cosine x, and let's take the derivative and set it equal to 0. We know that the derivative equals 0, the x value equal to 0 here at pi over 2, and down here at 3 pi over 2. So I went ahead and called the interval from 0 to 2 pi, and here at pi over 2, I left horizontal tangents, and here at 3 pi over 2, horizontal tangents. And then it was just a matter of test points, and we can kind of read these test points right after here. You guys know that between 0 and pi over 2, all these x values, which cosine is the x value, are going to be positive. So anything to the left are positive. We know that between pi over 2 and 3 pi over 2, that's this segment over here, this piece of the rotation over here, all those x values would be negative. So those are all downhill slopes in between the two. And of course, between 3 pi over 2 and 2 pi, all these x values over here are to the right of the y-axis, so they're all back positive again. So if, again, the slope kind of looks like the one up did before, not to mention the fact we know it looks like a sine curve, which we should know is the integral of cosine x, but it goes up, it maxes, it goes down, it mins, and then it comes up at the end. All right. So the other piece is 4.2 homework. I won't go through every one, but we'll go through maybe a couple of them. Using the sigma notation, we just plug in 1 first. And as we plug in 1 and then 2 and then 3 and then 4, then 5, we can add these all up and we get a summation of some sort. All right, you'll see the same things happening in 3. It's a little weird when we have a c in there, but that's just c plus c plus c. If we look down on 7, since it said go the other way, this is 1 over 3 times 1, 1 over 3 times 2, 1 over 3 times 3, all the way to 9. Must have been the lower bound was 1, the upper bound was 9, therefore 1 over 3i would have been the function. Gets a little more interesting as we go on here. This is maybe 11 is one to take a look at. You got 2 over n cubed minus 2 over n times a quantity of 2 over n. And then this one, the only difference in this last one, they only give us a couple, is 2n over n and 2n over n. So I guess I would tell you that this is a missing 1 here, and this is a missing 1 here, so therefore 2i over n cubed plus 2i over n. and this is a lower bound of 1 to an upper bound of n here in number 11. We're using some summation formulas in 15 and 17. So 1 to 20 of 2i, you can factor the 2 out front, and then this is just 1 to 20 of I, which is leave the 2 out front. 20 times 21 all over 2. So again, n times n plus 1 over 2 is the formula for I. If we had something like a binomial here, what you'd have to do is actually FOIL this out and then look at each of the pieces. So we've got summation of 1 to 20 of I squared. We brought the negative 2 out front, summation 1 to 20 of I, and then the summation 1 to 20 of 1. So I kind of tried to color code these and show you what the formulas look like as you come in here, but this is one to take a look at as for a typical example. All right, that's good for today. Thanks.